The objective of this video and next ones is to learn how to design the a wireless power transfer system. And the shown wireless power transfer system from Efficient Power Conversion Company basically consists of two printed circuit boards. The transmitter circuit board and the receiver printed circuit board. In the transmitter circuit board, essentially we have a DC to DC converter, which is implemented using the SIPC topologies that we discussed in one of the videos. And then this SIPC converter essentially supplies the power to a DC to AC inverter that we are going to see how to, or the basic operation of it in this video. And then we have essentially a DC block capacitor, resonant capacitor. And then this resonant capacitor resonates with the primary side coil of a transformer basically. So that's the transmitter side, or we can show it here. The transmitter side feeds essentially the primary side of the coil, and then we have in the receiver, embedded in the receiver, essentially the receiving coil of or the secondary side of the transformer. So basically what drives the transformer or the primary side is a DC to AC converter. Then in the receiving board, we have basically the receiving coil, and then resonant capacitors. And after that, essentially, we have a rectifier or AC to DC converter, and then another DC to DC converter that essentially provides a 5-volt DC to the electronic load. So in this video and next ones, we're going to see how to design the DC to AC converter as well as the wireless power transfer system. So what's a DC to AC converter? A DC to AC converter essentially is a power electronic circuit that converts DC power into an equivalent amount of AC power. Okay, so it changes the form of the electric power. So if we have 100 watt of DC power, a DC to AC converter is going to convert it from 100 watt power in DC form into an equivalent amount, almost 100 watt in AC form. So more specifically, a DC to AC converter converts the input DC voltage into an AC form or AC voltage. 60 hertz DC to AC converter that takes power from a solar panel. So the solar panel produces DC voltage. The output is DC. The DC to AC converter that takes this DC voltage and convert it into AC to interface with the 60 hertz voltage typically is called an inverter, power inverter. Okay, but generally DC to AC converters are, you can say, a DC to AC power converter, DC to AC inverter, or an inverter. So the DC to AC converter that drives the primary side coil in the wireless power transfer system is typically a series resonant DC to AC converter or series resonant inverter. So what are the components of a Class D series resonant inverter? Well, it consists of a half bridge, which is basically two switches, complementary switches. So when one switch is on, the other switch is going to be off, and vice versa. And these complementary switches are provided or supplied from an input DC voltage, VI, say, And they operate in complementary fashion with or via a 50% duty clock. So essentially the voltage that will be produced from these complementary switches will be a square wave or off square waveform with 50% duty cycle. And essentially this square voltage will swing between 0 volts and VI. So if we look at this voltage waveform in the frequency domain, we'll see that it consists, a square voltage consists of a DC component at VI divided by 2, and then from a fundamental component at a frequency, say F node, and harmonics, odd harmonics at the third, fifth, and so on, seventh, and so on. And so if we want to convert the DC to AC voltage sinusoidal, a sine function, at a specific frequency, then we need to filter this generated square voltage. So after the two switches, after the complementary switches, we have a low pass, or sorry, a band pass LC filter. The band pass LC filter is going to essentially be centered around the fundamental component and will have a frequency response as shown here, such that it extracts the fundamental sinusoidal component in this square signal. Okay. And then we have the AC load, RI. Okay, so basically a series resonant inverter that's typically used in a wireless power transfer system, in the transmitter side of a wireless power transfer system, consists of two complementary switches or a half bridge that essentially feeds that essentially provides a square voltage 50% with 50% duty cycle to a bandpass LC filter, second order bandpass filter, and then we have the AC load that basically this DC to AC inverter essentially supplies. Now, what's given? What are the given parameters for the design, and what are the unknowns that we need to design or essentially find? Well, first of all, we will know, or you will be given the input voltage, and you will be given the value of the AC load resistance, as well as according to the standards that will be used for wireless power transfer, you will essentially know the resonant frequency, or the frequency, the channels that essentially we're going to transmit the power across. So what will be the center frequency if node? And also, for simplicity, you will also know the quality factor. So typically the quality factor, so we said we have an LC bandpass filter that essentially its function is to extract the sinusoidal that's embedded within the generated square voltage. And to extract this square, you want the bandwidth of this filter to be small, such that it doesn't take the third harmonic. It only extracts the fundamental component and rejects the higher order harmonics starting from the third harmonic, right? And to do that, we know the quality factor of an RLC circuit is given by the ratio of the center frequency divided by the bandwidth. So the quality factor of this bandpass filter is given by its center frequency of node, where the bandpass filter is centered, and divided by its bandwidth. So if we need the bandwidth to be tight so that it extracts only the fundamental component and rejects the third harmonic and higher order harmonics, we need the quality factor to be essentially large. And from experience, we found that, or it's found that, the quality factor of an RLC circuit that's larger than typically 2.5 will essentially be able to extract or essentially reduce the amplitude of the third harmonic, such that the output of the bandpass filter is going to be almost a pure sine function that doesn't contain, or the third harmonic within that sinusoid is minimized. So typically quality factor is larger than 2.5. Now these are the givens: the input voltage, the DC input voltage, the load resistor, the center frequency, and the quality. Now what are the unknowns? Number one, what is the inductance that we need for the LC filter, as well as the capacitance? And of course, we know for an inductor there is an RMS current rating, there is a saturation current rating. And for the capacitor, not only the capacitance is unknown, we also need to find what will be the maximum voltage that this capacitor need to withstand or handle, as well as what is the maximum RMS current rating that the capacitor should handle. We also have an input decoupling capacitor, Cn, that we need to find its value. And of course, we have the switches S1 and S2. So we need to know their equivalent on resistance if we are designing a wireless power transfer transmitter that's basically using discrete components. If it's fully integrated on a chip, then we need to know what will be the width of the switches S1 and S2, because at the end of the day, R-on and the width, essentially, if you want a smaller R-on, you need to increase the width of the transistor. And of course, also transistors have ratings, so there is maximum voltage or voltage rating of the required voltage rating. What is the maximum current that the transistor should handle? Okay, so in total we have 6 main unknowns in the transmitter, in the design of the transmitter. So let's start by simply finding the value of the inductance and capacitance. We will worry about the rating, the RMS current rating, saturation current rating, and so on later on. And generally, to find these, we need to analyze mathematically or analytically analyze the DC to AC inverter. This one is a series resonant inverter. So, well, to find the values of the required inductance and capacitance, well, we are given the quality, right? The quality factor that we need to design. And typically, even if it's not given, we should use a value that's larger than 2.5 so that we minimize the amplitude of the third harmonic in the produced voltage from the resonant, the series resonant DC to AC inverter. So we know that the quality of a second order RLC circuit is going to be equal to the center frequency divided by its bandwidth. And so given the quality factor and the center frequency, we can find the bandwidth. an expression or the value of the required bandwidth as F node divided by QL. And then from the bandwidth, we know for a second order RLC circuit, the bandwidth is given by the load resistance Ri divided by 2 pi times the inductance L. And so from this equation, we can find the value of the required inductance L. Now, to find the capacitance, well, we know the center frequency of this second order filter or bandpass filter is essentially given by F node equal to 1 over 2 pi square root LC. And so after we find the value of L, we put it here, and the only unknown is C, and we can get the value of the required capacitance. Now, to be able to find the values of the required RMS current rating and saturation current, the ratings basically for the used inductance, and to find the ratings for the used capacitor, we'll need to analytically analyze the resonant converter. And to analyze the resonant converter, we need to get a simple equivalent circuit model for this resonant converter. So number one, well, the switches or the transistor S1 and S2, we know that we can model them, will have an equivalent on resistance. So basically we can model them by an ideal switch with zero resistance in series with a resistor with a resistance equal to RDS1, which RDS1 is equivalent on resistance of the top switch. Well, and similarly, the bottom switch can be modeled as an ideal switch in series with RDS2. And then we have the inductor L, but we know that an inductor will have an equivalent series resistance. Let's call it R small l. And also the capacitor will have an equivalent series resistance RC. And then we have the AC load Ri. Now, we can simplify that more by knowing that since we are generating a square voltage from the half bridge, so 50% of the time RDS1 is in the path of the current, and the other 50%, so 50% that's when S1 is on. S1 is conducting current, so 50% of the time the current is going through RDS1, and the other 50% the current is going through RDS2. And so we will find that the equivalent resistance of both of these resistors is going to be RDS, that's equal to the average value of RDS1 plus RDS2. And since each one conducts for 50% of the time, so we just divide by 2. And then we have the inductor L and its equivalent series resistance RL. Then we have the capacitor and its equivalent series resistor RC. Then we have the load resistor Ri, the AC load. Now, these are ideal switches that are turned on 50% of the time, complementary, in a complementary fashion. So essentially, we can just replace these by a square voltage source. And then we have ideal inductor L, ideal capacitor C, and then I could move RDS, RL, and RC in here. And let's just call them R, where R small is equal to RDS plus RL plus RC. And then we have the AC load Ri. And also for analysis purposes, we can add R small with Ri, and we call it R capital. So R capital is equal to Ri plus R small, where R small is RDS plus RL plus RC. And RDS is the average of RDS1 plus RDS2.